All right. Specifically for EMEA, here's what we did. The questions were 21. We're going to do 47 and 58. Those are the three homework assignments we did. We're going to scratch out 45. So let's go with it here. So we're going to try 47 on our hands here. Show of hands real quick here. How many did 47? Got it. Back the book and everything was fine. Ooh, okay, fun stuff. Okay, this is the connection between graphs and derivatives. Really a good way to sort of think through an understanding of it. From a graph perspective and trying to connect the numbers, which 45 also does the same. 45 is a good one as well. So let's go with it. 47, 47, 47. That one we are trying to find. F and G are the functions whose graph are shown. Let U of X be the multiplication between the two. Oh, we have another function called V of X. V of X is the quotient between the two. Okay, that's cool. Let's connect all these pieces together. So now A part is find U prime at 1. Whoa, how fun is that? Okay, so on the graph itself, 1 is right here. True, true. Is that right? About right there. Okay, let's jam with it. So first things first, I'm going to build my little function. I'm going to build the U prime of X. I got to build that one first. All right, and according to the product rule, I'm going to jump back over here, the way the book writes it. It's going to be the first function. I'm going to put these little prime numbers here. That's the derivative of G. The first function, derivative of the second function, plus the second function, derivative of the first function. That's the way it's customarily written. So now let's take a look at our little graph. Oh, sorry, hold on. So there's that piece. So now, once we take the generalized formula, generalized derivative, now we make it very specific. So it's going to be U prime of 1 equals F at 1, G prime at 1, which is the derivative at 1, and the function itself at 1, and then the derivative at 1. Woo, this will be fun, guys. So now, let's go with it one at a time. I'll let you guys finish writing down the derivative. Cool, okay. So let's look at our formula and let's go with it. What is the function of F at 1? You guys talk to me. So if we look at F as the reg function, correct? So if I say function at 1, all we got to do is figure out what's the Y value. So the question is, what's that dot right there? What's the value of F? 2, absolutely. The value of 2 right here. Okay, now the fun part begins. What's the derivative of G, the blue function, at 1? So notice it does cross right here, right? It crosses at 1, right? But we don't want the derivative. I'm sorry, we don't want the function itself. We want the derivative. Hey, real quick here, notice these guys are not curves. They're just lines, right? And don't lines have the same slope all the way through? Right, because if you go y equals mx plus b, right? That's your constant slope right there, right? And so we have that generalized formula. So guys, what is the slope of the blue line when it's right at 1? Not 1. No, that's the value of it, right? If you go g of 1 is 1, that's the value there. But I'm trying to figure out the slope. So what's the steepness? Is it going down or up, first of all? What do you guys say, down or up? It's going down, isn't it? So the slope has to be negative at this point, right? And can you guys calculate slope somehow? See again?
Yeah, is it 2 over 1?
2 over 1? I don't think so. So let's see. You guys talk to me here. This is getting scary. You guys talk to me. How do you guys find slope of a line that's y equals mx plus b? Okay, that maybe the, remember slope line was like this right here. What we did is we did y1 minus y2 and x1 or x2 minus x1, right? We simplify those, but really from a geometry perspective, don't we just do this? We go up and then we go over. So how much do you, oh, that's right. From geometry is rise over run, right? So how much do you go up or down? And how much do you go across? And once you get that, you're like, oh, that's cool. So we have to get 2 points anyways, but the line is the same, right? So at this point, I'm thinking like this. I'm thinking I'm going to start from this little 2 right up here, you guys. See if this makes sense. I'm going to go down 1. I'm going to go over 1, and I'm right here. So down 1 over 1, that's -1, true? So coming to the line, the slope is -1. And then also if I go from here, I'm going to go down 1 over 1. Notice the slope is still -1. Okay, we good? Cool, yeah. -1 is good. Okay, now the other one here. What's the value of g at 1? What's the value of g at 1? You guys talk to me. It's 1, absolutely. You got it right on. Okay, what is the derivative of f at 1? Ooh. Okay, now we're talking about, whoa. Now we're talking about the slope that's having from here to here. Notice it's the same slope, it doesn't change. What's the slope? How much do you go up from the corner to the other corner? Yeah, we can go 4 up, 2 over, or we can go 2 up, 1 over, 2 over 1. Rise over run is just 2. Okay, we're jamming. Okay, if that's the case, this is -2 plus a +2. Whoa, that's interesting. Slope is 0. Is that what it says in the back of the book? Just to make sure. So this was asking, what's the derivative of the product of these two? And there's no way we can get product stuff in here. I guess we can make equations align. That's going to go a long time here. But really the whole point here is if you can understand the derivative rule and then just start plugging in values from a graph. Got that? That's a good thing. Okay, let's jam with 47b. So v of 5. Okay, that's what we want to get. We're going to try to get, we need to get v prime of x first. Okay, it's a quotient because we go back over here. It's f of x over g of x. So that's quotient rule. So let's go to quotient. I'm going to go with g of x, f prime of x minus f g prime of x over g of x squared. That's what I'm looking for. All right, let's go with it here. Again, this is 5. So we're trying to look at where it's 5. So we're trying to figure out the value of g at 5, the derivative of f at 5, the value of f at 5, the derivative value at 5 for g, and then we're going to look at the value of g at 5 squared. Oh boy, let's jam. So 1, 2, 3, 4, 5. This is right before they touch. It's like right here. 5. Okay, you guys, since we did A, V is easy. Let's go with it. Anybody give me a value of G at 5? All right, everybody agreed it's 2? Value of G at 2? Okay, I'm going to pick on people now. Haley, that was a volunteer for her. Now we're going to go across. So Chris, Nicholas, Chris, sorry, still waking up. It's before 8. I get an excuse. Nicholas, give me the derivative of f at 5. What's the slope of that line coming down? That is awesome. Yep. The path is 1/3. Don't think it is going down negative. So got myself a negative 1/3. 1 down, 3 over to get to the next little crosshair piece from there. Good job, Nicholas. That was awesome. At the negative there. Zachariah, f of 5. 3 is cool. Back to Haley. Give me the derivative of g at the 5 level. Ooh, they're trying to mess with you because not even a crosshair, huh? Gotta figure which 2 crosshairs does it hit. Let's see. So I'm looking at, let's see what we're looking at. We're looking at 5 here. We're trying to get the slope of the blue line, correct? So I'm thinking here, I'm going to use this point here. And as I go up, Yeah, right at 5, it hits another crosshair point. That's one that it hits, the other one. So now I'm thinking, okay, I'm going to go up 1, 2, looks like. And then in order to get to that, 1, 2, 3, 2 over 3, perfect. Okay, doo-doo. Back to red. 2 over 3 it is. Okay, and then this one we had already before, right? Isn't that like 2? Yeah, it's 2. For the second, we did it right over here already. Sweet, okay. Okay, that was the calculus portion right there. You guys get the pre-algebra portion right here. And simplifying this. So you got to simplify the top as much as you can. And then we're going to do something called keep, change, flip. Or keep, change, reciprocal. Negative 2/3 minus 2 common denominators. Okay, let's see what I got here. The 3's canceled here, so that just left the 2. Then I still have a denominator of 3 over there, so then that 2 changes into 6 over 3. You guys okay with me on that one? Okay. I got negative 8 over 3 all over 4. I'm going to change it to 4 over 1, which makes negative 8/3 multiplied by 1/4. Sorry, would you guys do that? Just checking my answer, make sure that we're correct. Oh, that should be correct by the time we finish it up. 4 and 8 reduce by 4, so that becomes 1 over here on the bottom. That becomes a negative 2. And final answer, 2/3 is what the back of the book said as well. Negative 2/3. Thank you. All right, 58. This one we have to do, it's an even problem, so you guys don't have answers to it. This one I did want you guys to have it as another repertoire of derivatives. We did not give it to last year's students. So in calculus, we deal with these quick rules, right? The quotient rule, right? As opposed to going all the way back to the definition and recycling this all the time, right? So it's really just what's the expedient way to get here? And so we could make up a whole bunch of different rules. But mainly we have the product rule, the quotient rule, something called the chain rule, which we'll look at later. And we do have to do all the trig rules as well. And we have the power rule, right? Oh, hold on, we got another one. Then we have the e to the x rule, which is itself, right? Then we have to get the logarithmic rule. And so, and those are, if you kind of distinguish the trig rule, exponent rule, e to the x rule, those would have to deal with specific functions, right? Then you have the generalized rules, which is the product rule. It can work for any function, quotient rule, any function. The power rule kind of is in between, right? Because the power rule works for a certain kind of function, right? They kind of put on the function scale. Okay. But the question is this: is there a quick little rule that I can to do that right there? Do I have to go back to the power rule? Do I have to go back to the quotient rule? And so it's just another extra little rule you develop for yourself and say, oh, I can take a derivative of this really, really quick. So what we have to do is we have to prove that it works. So we're going to do this here. We're going to say, let me take the derivative of 1 over g to the x. I'm going to do it by quotient rule first right now. But once I'm done, I'm going to have a little formula for myself. So let's go with it here. So I'm going to go off to the side. And I'm going to rewrite my quotient rule real quick here. Quotient rule is g f prime minus f g prime over g squared. That is just kind of off to the side real quick here. Boom. You guys will write that a lot. By the time you finish, you guys will be experts in rewriting the quotient rule. Okay, so let's do this here. What's the derivative of 1? I think that's a constant, huh? That's a constant. 0. Awesome. Okay, as I do this here, I'm going to go have g of x as a function itself multiplied by 0. Whoa, that's 0. That's gone. Minus the f function, which is 1. This would be the derivative of 0 this time over g of x being squared. Okay, can we simplify this guy? Absolutely. That goes away. That's 0. We have a little negative here. So this would be a negative here. The derivative goes on top. And squared goes on the bottom. Are we good there, guys? Yes, we have just developed the reciprocal rule. Okay, so what do we do with the reciprocal rule? If we see 1 over a certain function, we stick a negative in front, we take the derivative on top, and we square it on the bottom, and we're good to go. Easy, as opposed to just doing the whole entire. Now, Sadie, she's smart. She kind of can pick that up. She already knew that. Okay, so now let's do this here. Let's go back to number 18. Let's do an easy one first. This is 18 gets all crazy real quick here. Let's do that. Let me pick another one. So it has to be 1 over something, right? Because the reciprocal has to be 1 over. Let's just do this one real quick here. Let's take the derivative of, do an easy one here. Here it is, 1 to the 4th, we were talking about earlier here. Okay, ready? Let's be quick. Boom, I see 1 over something, 1 over x to the 4th. Here it is, I stick a negative in front. The derivative of x to the 4th, anyone? X to the 3rd, perfect. That same function squared. And go ahead. Like, see, 16. We're gonna go with 8 because remember exponent rules. Yeah, it's multiplying. No problem whatsoever. You got 8 here. Boom, and now we're gonna do. We got 3 on top. We got 8 on the bottom. We're gonna do the quotient rule for exponents, right? So if we've got 8 on top, 3 on top, 8 on the bottom, it's gonna be a subtraction between the two. 3 minus 8 is 5. And so the bottom's gonna win. So we got ourselves x the 5th. Okay, guys, talk to me. Was that easier than doing the quotient rule? I think so, because quotient rule takes a long time. Okay, is that probably good there? Sweet. Okay, now we're gonna do the crazy one. Can you guys give me or take the derivative of, using this reciprocal rule, I need, oh, let me rewrite it again over here. Y equals, just written differently, 1 over s plus k . Is that an S right there? Oh, it's an S. Okay, S right over here. I thought it was a 5. That's an S, is that right? Okay, guys, I'm thinking S is our variable because K usually means constant. So off to the side here, I'm gonna go like this. I'm gonna go boom. What's the derivative of this guy? All right, give you guys 30 seconds. Try it yourself. The derivative of that, it's so 1 over S plus K e to the S. Here. Okay, you guys talk to me here. Let's see. Zachary, you're finished first. I'm gonna pick on you here. What do we do? Okay, so the derivative of S is 1, right? The K still stays there and e to the S. Perfect, okay. We gotta get a negative in there too, right? So negative goes right over here, boom. Thank you, Zachariah. And then we got ourselves the bottom was exactly the same, except taken to the second power, done. That is so much easier than taking the quotient rule. Okay, everybody good there? Okay, awesome. Okay, with time remaining, let's jam with it here. So we have 3.3 is what we begin now. All right, the fun stuff. It's all fun. There's I mean, it's his math is all fun until someone divides by 0. Derivatives of trigonometry. Function. Okay. Let's jam. Okay, so page 189 is where we're at. Everybody have a book in front of them. That's cool. So let's jam with it here. So first things first, we need to get this whole concept of two things that come up for us. And just kind of, we have to understand you. Oh, let's do this here. So 189 is when we begin. We're going to look at the derivative of the sine function. Good. So remember, the sine function is just the slopes, right? So turn the page over, and we have ourselves the sine function. And notice, again, this connection between graph. Notice the top graph. Notice it hits a slope of 0 at pi over 2. You good? So notice the blue line compared to the red line. So the slope is the point now at pi over 2. So any time you get a horizontal slope, that becomes a time where it hits the x-axis with a 0. You're good there. And also notice at the top graph, right at x equals 0, right at x equals pi, it swoops down and it actually becomes 1 or -1. Isn't that cool? So it bumps up to 1 as a slope as the high still goes down to 0, goes into the negative range, hits a -1, comes back up to 0, comes back up to positive, and goes, and it keeps on cycling this all the way through. Okay, guys, talk to me. What does the bottom graph look like? It's what? It's cosine. It's the cosine curve. That is crazy. Okay, so the derivative of sine is actually cosine. So now the question is, how do we prove that? There's a proof of that. And so the proof is down here, but let's go through the proof, and then we'll, just for sine, and then we'll jam with the other ones here. Okay, so notice on the calculator, you can do this on a calculator. If you start taking the derivative of cosine, you look at the times where it hits the 0 marker, you place them as zeros, and we'll do that. If we have time, we'll do that. And if not, we'll do a little bit later. Okay, so let's jam with the proof. Proof. We looked at a graph already. Proof that the derivative of sine is in fact cosine. Right there. Okay, let's jam with it here. So first things first, the definition. I think I remember this one, right? The definition for the derivative. We'll add in a few more things the book does not get to here. So I think this is the definition for derivative. Tell me if you guys think yes or no here. It is f of x plus h minus f of x over h. I believe that's the derivative. Yeah, that's cool. Okay, so our function is sine of x. So let's just plug in the sine of x into this guy. So limit as h goes to that. This is going to be sine of x plus h minus sine of x over h. Do you guys remember back to trigonometry? What is sine of x plus h? What's the addition formula for sine? Or if you don't know it, you just quickly go back to the front of your book. That's what I want on top. I want the root. All right, if you flip to the front of your textbook, some of you guys have formulas there. Look at that. Mine's not cool. It does not have the formula. It says, Mr. G, you don't get a formula. Okay, so you guys have to help me here. The addition angle property for sine. Perfect. Okay, so cosine of x, then it flips to the other side, which is cosine. You guys talk to me. Did you guys ever find it? Is it on the front cover or the? You guys have it there? Nicholas, did you find it? Is that correct? Did you find it? Yeah, so it's the addition angle formula for sine. Sine of, it has x plus y for the addition formula, right? So your y is essentially your h. So sine of x, cosine h plus, I think it's a plus sign, right? Plus sign, yeah. Then you flip it. So cosine of x, sine of h, I believe. Yep. Minus sine of x. Okay. We're jamming. Okay, so I noticed a couple of things here. I notice, oh, you know, I noticed I have a sine of x right in the beginning, and I also have a sine of x all the way at the end. Everybody okay there? Okay, so let's do this here. I'm going to move this guy over here to this side. I'm going to split this up. You guys tell me if you guys agree with the split up, okay? So I'm going to do this here. I'm going to say h is going to be over here. I'm going to get all the sine of x's together over here. Oh, that's a minus sign here, boom. And the cosine x, that's just going to go off by itself. I'll do that. So I just kind of move this little negative sine x over here. And I split the fraction. You got it? Okay, you got it. Okay, so now let's see what's happening here. Limit, now I'm going to split the limit into each one of these guys here. The limit goes to this one. Not much of a change here. Plus the limit as h goes into this one. Da, da, da. Okay. Cool. And I see something interesting. You guys look at this. Our h is our problem, isn't it? If a function has x inside it, is that our problem? No, because if it doesn't have an h, I can move it around. It's almost like a constant. You good? It's almost like a 5. So I see sine of x right here. And I see sine of x here. I'm going to take sine of x out, and then I'm going to actually take it out in front of the limit function because it doesn't belong to the limit. Only h is taking a limit. So let's do that here. Got to go on to the next slide here, but I'm going to go like this. Sine of x gets all the way to the outside. Limit as h goes to 0. Let's see what it's just for the cosine of h minus 1 over h. That's what the limit's for. On the other side, what do I take out? Cosine, absolutely. Cosine gets to nicely go out. And our limit is only dealing with the h. And if you want to put parentheses around it, that's fine. If you don't, that's fine too, because it's all one quotient after the limit. Okay. Now I'm going to have to jog your memory here. You guys, we have done this limit before already. And we have done this limit before already. That was in chapter 2 when we started limits. I'll even reference 2.2 is actually what we did. So let's see in our books. Let's go back to 2.2. Example 3, that's what we're looking for. 2.2, example 3. Example 3. Oh yeah, it's on page 91, yeah? That's when we're looking at funny limits. So notice we did it by table, right? Because we were just being introduced to limits here. So I'll get you guys to page 91. And off to the side of your page, in that blue stuff right over there, off to the side, it says x and it says sine of x over x. Blue stuff on the side. Notice if I go from 1, then 0.5, 0.4, 0.3, 0.2, 0.1. From the positive side and the negative side, it goes 0.84, 0.95, 0.97, 0.99, 999, 999, 99, 999, 999. What is the limit approaching? It's 1. So this guy here is a 1. Awesome. And I'm going to put this in cosine of x. Okay, everybody good there? So this one, we didn't do it by limits. I mean, we did it by a table. We found out the limit is 1. Okay. The other one. We also did the other one as well. How did we do that one? I'm trying to figure out. We did it by, the book says we didn't do it. I know I did it in lecture. Because I said, hey, how about this? And we kind of did it the same. We did it by table again, I believe. Let's see, probably not gonna find it now here. Let's do this here. We're gonna do it from 2 different spots. We're good. If you want to jump to page 191 in the textbook, 191 in the textbook, it does have a proof for it, just a quick little proof. 191, all the way in the bottom of the page. It says the limit as theta goes to 0 of cosine theta minus 1 over cosine, or sorry, over theta. And then it has this little sneak little thing of multiplying the cosine theta plus 1 on both sides. And then it cancels off, and eventually, what does this go to? There it goes to 0. We good? So this becomes 0 over here. This is sine of x multiplying times 0. I think we finished off our proof, guys. Look at this. That's 0, so that's going to go away. I'm left with cosine. So the graph was cool to look at, but graphs are really not proofs. You need kind of like the algebra proofs. You need the geometry proofs to get you to that connection here. So there it is. The sine, the derivative of sine is cosine. Okay. So now let's flip. Again, I do want you guys to read this over, right? Again, let's kind of flip through the pages now. So 192, example 1. 192, example 1. Now we're actually dealing with the derivatives, right? Y is equal to sine squared, sorry, x squared times sine x. Voila. That looks like a product rule to me, doesn't it? And then it's just, so we start using it here, okay? Let's go through each of the red rectangles here in the book real quick here. So go on that number 5 rectangle. It says the derivative of cosine is negative sine. That's cool. So hold on. So if I have derivative of cosine is negative sine, can I take the derivative of sine again? Can I take the derivative of negative sine now? Oh, hold on. I think I got something here. So let's see. If I go sine here, come on, goes to cosine, and this is kind of like derivatives, right? This guy goes to a negative that. You guys talk to me. What should be the next one down? Negative cosine, yeah, because the sign doesn't change, right? It can be like a multiplier on front. So hold on, this is negative cosine. And hold on, and let's go to the next one now. It's the negation of this one. Whoa. It's the negation of this one, right? So it'll be a negative of a negative sign, which is just positive sign, and the whole thing starts all over again. We good? At a cycle of 1, 2, 3. It has a 4 cycle of 4 right here. Whoa, so these guys go on forever. Okay, boom. They do one for tangent as well. The derivative for tangent, and then they list all of them on page 193. They list all the trig functions. There they are. And then example 2 is a quotient rule involving trig functions here. There it is, just quotient. Example 3 is a physics rule as we jump to the next one. And take a look at that physics rule, because I think we're ready for those. S is for position. T is in terms of time. And then they want you to take and find velocity and also acceleration. Let's see what that looks like. And then example 4 is something that we talked about just now, which is the derivative. You can take the 27th derivative of cosine if you like. And you just go for it here. Okay, and then we've got some extra limits. Now that we know specifically that we know this little guy right here, because in limits in chapter 2, we limited ourselves to limits. We didn't find all of them. In fact, as you progress, or if you progress later on in calculus, you guys will find even more limits. There's a whole world of limits out there. Okay, but now that we know that the limit as theta goes to 0 of sine theta over theta is equal to 1, and the other one goes to 0, we can find a whole bunch of different limits now. And that's what examples 5 and 6 are all about. And then we go from there. We're good? Cool. All right, that should be enough to get you guys started with it. And did I include the physics? Yeah, I included the physics problem. A little bit different. It's about a ladder. But a physics problem in text. Okay, let you guys try those. Come back on Wednesday, and we'll handle something called the chain rule. Yeah, just a few more things to deal with here. So chain rule, another generalized formula, implicit differentiation, another one, and then we'll jump to a log, derivatives of regular log functions. And then we'll be done with chapter. Well, then we're ready to take a test. So we're ready to take a test after Christmas break.